One, we start with the trigonometry. So if you have the integral of dx over square root of 1 minus a squared x squared, then you are supposed to get 1 over a sine inverse of ax, of course, plus your arbitrary integration constant. If you integrate dx over square root of 1 minus a squared x squared, then you're supposed to get 1 over a sine inverse of ax plus c. Are we together? Now, this is a standard integral. So a standard integral is something you don't integrate, isn't it? You have to master it. So how does it come about? So let us say from differentiation, for instance, when you have y to be equals to the sine inverse of ax, isn't it? To differentiate sine inverse, you must get rid of the sine inverse function, isn't it? Meaning the derivative we are supposed to get here is we are differentiating y with respect to x, isn't it? So the derivative here is dy over dx. But we cannot integrate an inverse function, so sine inverse we have to bring it this side, isn't it? So it means sine y is equals to ax. If you want to get rid of the inverse function, when it comes this side, it becomes sine y, isn't it? So sine y is equals to ax. So from here, we have ax is equals to sine y. So it's like we are integrating x with respect to y, isn't it? A is a constant. If you differentiate x with respect to y, you get dx over dy, isn't it? If you differentiate x with respect to y, because a is a constant, you get dx over dy, isn't it? If you differentiate sine y with respect to y, remember we are differentiating both sides of the equation with respect to y, isn't it? If you differentiate sine y, you get cos y, then you remain with dy over dy, isn't it? Which is 1, isn't it? So from here, what do we want? We want dy over dx, because that is the derivative, isn't it? Dy over dx. So if you take a the other side, if you divide both sides by a, you get dx over dy is cos y over a, isn't it? So from there, you find the reciprocal on both sides. You get dy over dx is a over cos. So you can see dy over dx is the derivative, isn't it? Yes. Dy over dx is the derivative. Then now, we want everything, because we were given sine inverse of x, meaning everything must be in terms of x, meaning we get rid of cos y, isn't it? We use Pythagorean identity, because we know that cos squared y plus sine squared y is equals to 1. But you know sine y, meaning you can write cos y in terms of sine y, because sine y is ax. Are you seeing? Sine y is ax. So for you to get cos y, what is cos y? Is 1 minus sine squared y, then square root of that. You take sine squared y, the other side you get y minus sine squared y, isn't it? Then for you to get cos y, you find the square root on both sides. Are you seeing that? Yes. So from there we have the square root of 1 minus, what is sine y? Sine y is ax. So if you square both sides, you get sine squared y is a squared x squared, isn't it? So you have 1 minus a squared x. So it means where there is cos y, we are going to put square root of 1 minus a squared x, isn't it? So here we have dy over dx is equals to a over square root of 1 minus a squared x squared, isn't it? Now look at this. From here, what you do here is now very simple. If you take dx the other side of the equation, we remain with dy is equals to a dx over square root of 1 minus x squared, isn't it? Are we together? So from there, if you introduce the integral on both sides, what do you have? The integral goes with you remain with y, because it's like you are integrating y raised to power 0, you remain with y, isn't it? So here you remain with y to be equals to the integral of a dx over square root of 1 minus a squared x, isn't it? But what is y? What is y? Y is sine inverse of AX, meaning if you integrate A dx over square root of 1 minus A squared x squared, you get sine inverse of AX, you get Y, which is sine inverse of AX. But now you see, A is a constant, can be factorized outside the integral, isn't it? Are you see? Yes. Are we together? So if you divide both sides of the equation by A, because here is 1, coefficient of 1, isn't it? If you divide both sides of the equation by A, what do you get? You get, if you integrate the x over square root of 1 minus A squared x squared, you are supposed to get 1 over A sine inverse of AX, then plus your arbitrary integration constant in case of indefinite integral without limits, isn't it? Are you seeing that? So it means, for you to know how to get the derivative of this inverse function, all you have to know is that, for you to know the integrals of this kind of function, you have to know the reverse process in differentiation. Now you are differentiating inverse function, isn't it? Then when you do that reverse process, you get that, right? The corresponding integrals. Are we together? So that is how to deal with the integrals of, how to get the integrals of inverse functions. So let us look at part B. That is the first one, A, B. B. If you have the integral of dx over 1 plus A squared x squared, you are supposed to get 1 over A tan inverse of AX, of course, plus your arbitrary integration constant. So if you integrate dx over 1 plus A squared x squared, you're supposed to get 1 over A tan inverse of AX plus C. Are we together? Now you just come from the differentiation process, the way we were doing it. If you have y to be equal to the tan inverse of AX, then it means if you differentiate y with respect to x, we are supposed to get dy over dx as the derivative, isn't it? So if you get rid of this tan inverse, if you bring it this side, what do you have? Tan inverse of tan y, tan inverse changes to tan, isn't it? Yes. Tan y is equals to ax, isn't it? So it's like ax is equals to tan y if you swap. So we are differentiating both sides of the equation with respect to y, isn't it? Or with respect to x, whichever. Then later on we'll cross multiply to make something the subject of the formula, whichever, isn't it? So with respect to y, a is a constant. If you differentiate x with respect to y, you get dx over dy, isn't it? If you differentiate tan y with respect to y, the derivative of tan y was x squared, isn't it? With respect to y is dy over dy, that is silent, isn't it? So from here, you can see, if you take a the other side, you divide both sides of the equation by a, what do you get? You get dy over dx is equals to a over sec squared y, isn't it? But remember, we know tan y is ax. So if tan y is ax, meaning if you square both sides of this equation, you will definitely see that tan squared y is a squared x, isn't it? So you see, you can eliminate sec squared y using Pythagorean identity, isn't it? Because Pythagorean identity, what do you know? The second Pythagorean identity, sin squared y plus 1 is equals to sec squared. So that's the second Pythagorean identity. Yes. Tan squared y plus 1 is equal to sec squared y. But what is tan squared y? A squared x squared, isn't it? So a squared x squared plus 1 is the same as 1 plus a squared x squared to be equals to sec squared y. So where there is sec squared y, you put 1 plus a squared x, because that is 1 plus tan squared y. It's the 1 plus a squared x squared, because tan squared y is a squared x squared, isn't it? So if you substitute say that, what do you get? Dy over dx is equals to a over sec squared y, which we found to be 1 plus 1 plus a squared x squared, isn't it? So from there, you take the x the other side of the equation. So you get dy is equals to a dx, isn't it? Over 1 plus a squared x squared. Then you put the integral on both sides of the equation, isn't it?
Yes.
So if you integrate dy, you remain with y to be equals to a is a constant, you take outside, then we have the integral of the x over 1 plus a squared x squared. But what is y? Tan inverse of ax, isn't it? Tan inverse of ax to be equals to a integral of the x over 1 plus a squared x squared. So if you divide both sides by a, you get 1 over a is equals to that, isn't it? So in the end we have that the integral of the x over 1 plus a squared x squared is 1 over a tan inverse of ax. So it means that when a is 1, then you can simply clearly see that when a is 1, then dx over 1 plus x squared, isn't it? Dx over 1 plus x squared is equals to tan inverse of x, because 1 over a will be 1 over 1, which is 1, isn't it? Are we together there? Okay? Good. So that is a case of the tan inverse function. Then in trigonometry, the last one, there's no need of looking for, you will never look for the cosine, the cos inverse of x, because the cos inverse is always the negative 1 over square root of 1 minus a squared x squared. But in integral, you can factorize out negative, isn't it? So when you factorize out negative, it means it now goes back to the sine inverse function. Are you seeing? So we don't need a cos inverse function. Are we together? It doesn't work here, because when we took out this negative, we factorize out whatever is remaining inside is a sine inverse function. Are we together there? We don't need a cos inverse function. At the same time, we don't need a cosec inverse function, because if you took it out this negative, that one remains a sec inverse function, isn't it? So can we now look for the sec inverse function? Now, these are standard integrals, meaning there are things you need to do. There are things you need to know, not things you do, isn't it? There are things you need to know, then you use to solve a given problem, isn't it? You know them, then you use them to solve a given problem. If you are given that y is equals to the sec inverse of ax, let's start from here to find it. It's usually something like, I don't know, 1 over x into square root. We are going to see it, okay? So if y is sec inverse of ax, what do we have? If we bring sec inverse to this side, we get sec y is equals to ax, isn't it? Meaning here, our derivative here is dy over dx, because we are going to differentiate y with respect to x, isn't it? But we cannot differentiate an inverse function, so we bring sec inverse to this side, so we get sec y is equals to ax. So if you differentiate sec y, what do you get? Tan y sec, a standard differential. You don't need to do it, something you know. Are you now getting what I'm trying to say? Yes. You get tan y sec y with respect to y. dy, you remain with dy over dy, isn't it? Silent, then it's a constant. If you differentiate x with respect to y, you get 1, you remain with the dx over dy, isn't it? That one, when you differentiated both sides of the equation with respect to y, isn't it? Here you remain with the dy over dy, which is silent. Then here you remain with the dx over dy. So you bring your a this side, divide both sides of the equation by a. So what do we remain with? Dx over dy is equals to tan y sec over a. Then we want dy over dx, because that is the derivative, isn't it? We find the reciprocal on both sides of that equation. So it means dy over dx is equals to a over tan y sec y, isn't it? Then you start, you take dx the other side, isn't it? So if you take dx the other side, we remain with dy is equals to a dx over tan y sec sec y, is it? Everything here, because we have sec inverse of x, meaning tan y sec y must be in terms of x, isn't it? So already we know sec y, we already know sec y is ax, meaning where there is sec y, we are going to put ax, isn't it? So what we need to look for is tan y, isn't it? How do we get tan y? Pythagorean identity, isn't it? So we know that tan squared y plus 1 is sec squared y. Pythagorean identity, isn't it? So this one means that tan squared y is equals to sec squared y minus 1, isn't it? So we have tan squared y is equals to, what is sec squared y? If sec y is ax, meaning sec squared y is a squared x squared, you square both sides, isn't it?
Yes.
So this one is a squared x squared. If you square both sides of this equation, it will imply sec squared y is a squared x squared, isn't it? If you square both sides of the equation, isn't it? So tan squared y is x squared minus 1. So for you to get tan y, you look for the square root on both sides, isn't it? So there you have tan y is equals to square root of a squared x squared minus 1. Are we together there? So where there is tan y, you put square root of a squared x squared minus 1. Where there is sec y, you put ax. So if you substitute, what is dy? Dy is a dx over sec y, we found is ax, and y we found is square root of a squared x squared minus 1. So you can see a cancels out with a. Are you seeing that? A cancels out with a. So what do you remain with? A cancels out with a. What do you remain with? You remain with the dy is equals to dx over x square root of a squared x squared minus 1. So if you introduce the integral on both sides of the equation, if you integrate dy, you remain with y, isn't it? Are we together?
Yes.
So you get y is equals to the integral of dx over x into square root of a squared x squared minus 1. So what is y? Y is sec inverse of ax, isn't it? So where there is y, you put your sec inverse of ax. So it means when you integrate, when you have integral of x into square root of a squared x squared minus 1, then the answer is supposed to be sec inverse of ax, then plus your arbitrary integration constant. So when you integrate 1 over x into square root of a squared x squared minus 1, you get sec inverse of x plus. So you see there is no 1 over a. Have you seen that? There is no 1 over a. So that is how to get a sec inverse function as the result of the given integral. This was part C. Let's go to number 4. We are now going to hyperbolic functions. We want to see how hyperbolic functions behave. We now go to hyperbolic functions. So before we go to hyperbolic functions, these are standard integrals you need to know. We've said when you have the x over square root of 1 minus a squared x squared, you are supposed to get 1 over a sine inverse of ax, isn't it? Then we've also found out that when we have the x over x into square root of a squared x squared minus 1, then you are supposed to get sec inverse of ax plus c. For the sec inverse, there is no 1 over a, isn't it? Then we've also found that when you have the x over 1 plus a squared x squared, then you are supposed to get 1 over a tan inverse of ax plus c. These are standard integrals. You don't need to do them, you use them. Are you seeing that? Those are standard Integrals. Let's go to the hyperbolic. We see the hyperbolic, how the hyperbolic standard integrals behave. This one's we've already written in what we were deriving. So hyperbolic start with the first one. If y is tan inverse of ax. Hyperbolic ones are very simple. So here, it means if we differentiate, we get dy over dx. We differentiate y with respect to x, we end up with dy over dx, isn't it? So to get rid of the inverse function, we bring it this side of the equation, isn't it? Yes. So if we bring it this side, we have tan y is equals to ax. Are we together? Yes. Can you now differentiate both sides with respect to y? Introduce ddy on both sides. If you differentiate as y with respect to y, you get sec squared y. That was a standard differential. You don't need to confirm that is something you mastered, isn't it? Yes. You get sec squared y, then you remain with dy over dy, which is silent, isn't it? Yes. To be equals to a is a constant. If you differentiate x to get 1, you remain with dx over for differentiating x variable with respect to y variable, isn't it? So here, our answers will be dy over dx. So it means this a, when it comes to this side, you divide both sides by a. So you remain with dx over dy is equal to sec squared of y over a. So if you turn them upside down, you get dy over dx is a over sec squared y, isn't it? If you find the reciprocal on both sides of the equation, isn't it? If you find the reciprocal on both sides of that equation. Now from here, you take dx the other side of the equation, isn't it? So you remain with dy is a dx over sec squared y, isn't it? Are we together? So from here, you get rid of sec squared y, isn't it? Yes. The first Pythagorean hyperbolic identity, what do you have? When you have cos squared y minus sec squared y is equals to 1, because a direct product of two same functions change the sign to negative in hyperbolic, isn't it? Yes. Are you seeing that? So for you to get sec squared, it means we divide all through by cos squared, isn't it? You divide all through by cos squared y. Cos squared y. So cos over cos is 1 minus sin over cos is tan squared, isn't it? 1 over cos is sec squared, isn't it? So from there, you know where you introduce it. Here is where we had tan y to be ax. Meaning, when you have tan squared y, that is a squared x squared, you squared, isn't it? Are we together? Because tan y was ax, meaning if you square both sides of this equation, you get a squared x squared. So this is 1 minus a squared x to be sec squared y. So where there is sec squared y, you put 1 minus a squared x squared. Where there is sec squared y. Have you seen that? Yes. So it's like we have dy is equals to a dx over 1 minus a squared x squared. Are we together there? Yes. 1 minus a squared x squared. So from here, introduce integral on both sides of the equation. If you integrate dy, you remain with to be equals to a into integral of dx over 1 minus a squared x. Are we together? So if you divide, what is y? Y is tan inverse of ax. So where there is 1, you put your tan inverse of ax to be a into integral of dx over 1 minus a squared x squared, isn't it? So if you divide both sides by a, it means that if you integrate 1 minus a squared x squared, you are supposed to get tan inverse of ax. Of course, plus your beta integration constant if you don't have a limit in case of an indefinite integral. If you see such a case in exam or anywhere, then it results in the tan inverse of ax. Let's go to the fifth one. So that is the fourth one. Very important. Let's go to the fifth one. I need to first show you how they come about because there are things you need to master, okay?
Yes.
There are things you need to master. The next one, we dealt with the tangent inverse. We move to cos. Or before that, we can say when you have y to be sec inverse of ax. When you have sec inverse of ax, what do you get? Y is equals to sec inverse of ax. What do you have? Doing sec inverse this side of the equation, you have sec y is equals to sec y is equals to a. Are we together? Yes. Sec y is equals to ax. So if you differentiate sec y, you get tan y sec y standard. If you differentiate sec y, isn't it? You get tan y sec y. Then you, with respect to y, you get dy over dy. Then here, if you differentiate x with respect to y, you remain with the dx over dy. You get 1, then you remain with the dx over dy, isn't it? Are we together?
Yes.
So from there, as usual, our derivative is supposed to be, you are differentiating y with respect to x, meaning our derivative is supposed to be dy over dx, isn't it? So if you take every side of the equation, we remain with the dx over dy is this. So if you look for the reciprocal on both sides of the equation, you have a over tan y sec y is supposed to be y over dx. Are we together?
Yes.
So from there we substitute for tan y and sec y. So first of all, what is sec y? Sec y, you know, is that, isn't it? So this implies that sec squared y is a squared x squared, isn't it? Are we together? Then, what is tan y? Pythagorean identity, isn't it? Pythagorean identity, when you have 1 minus tan squared y is equals to sec Pythagorean identity, isn't it? Are we together? So from there, what do you see? We want to make tan squared y the subject. You take that side, you bring sec this side. So you have 1 minus sec squared y is tan squared. If you take my negative tan squared y, that side becomes positive. If you bring sec squared, this side becomes negative, isn't it? Are we together?
Yes.
So what do you get? The square root on both sides. So you get square root of 1 minus a squared y, but sec squared y is a squared x is equals to square root of tan squared y, which is just tan y. Are you seeing that? Can you now do the substitution? Where there is tan y, you put the value of tan y. Where there is sec y, you put the value of sec y, isn't it? So we have here, we have a over sec y, we found is ax tan y, we found is square root of 1 minus x squared to be equals to, if you bring dy over dx, isn't it? To be equals to dy over dx. So if we multiply both sides by dx, we get a dx is equals to dy, isn't it? Are you together? So from there, a cancels out with a is common, isn't it? See, a in the numerator cancels with the one denominator, because there's multiplication between here. So that one goes, you remain with this. So if you introduce integral on both sides, then you find out that the integral of dx over x into square root of 1 minus a squared x squared, you are supposed to get, if you integrate dy, you get y, isn't it? You're supposed to get y. But what is y? Y is sec inverse of
AX.
meaning where this is where you put the value of y, which is sec inverse of ax, of course, plus USC at the end of integration. So it means if you integrate dx over x into square root of 1 minus a squared, you get sec inverse of ax. When it was sec inverse of ax, it was the reciprocal inside, it was the opposite inside, it was a squared minus 1. Are you seeing? Isn't that? Okay? Are we together? Move to the last one, or to the second last one. When you have y to be the sec inverse of ax, if you have y to be the sec inverse of ax, meaning here, if you differentiate y with respect to x, you are supposed to get dy over dx. So to differentiate an inverse function, you bring tan inverse this side of the equation, sec inverse. You get sec y is equals to
AX.
So if you differentiate both sides with respect to y, differentiating sec y, you get cos. Differentiating ax, you remain with the dx over a is a constant. If you differentiate x, you remain with 1. Then you are differentiating x with respect to y, you remain with the dx over dy, isn't it? Here you are differentiating y with respect to y, you remain with the dy over dy silent, isn't it? So from there, you can now see, if you find, you divide both sides of the equation by a, you get cos y over a is dx over dy. You look for the reciprocal on both sides of the equation. A over cos y is dy over dx, isn't it? You bring dx this side of the equation, you get, if you multiply both sides by dx, you get a dx over cos y is equal to dy. So this cos y must be in terms of x, isn't it? So what do you know? That is Pythagorean hyperbolic identity, isn't it? Where cos squared y minus sec squared y is equals to, so for you to get cos squared y, you take sec squared y the other side, isn't it? So you get cos squared y is 1 plus, are you seeing that? 1 plus sec squared y. Okay? So sec y is ax, meaning sec squared y is going to be 1 plus ax squared, isn't it? So that is 1 plus a squared x squared. That is cos y. So you found cos squared y is 1 plus a squared x squared. You look for the square root of both sides for you to get cos y, isn't it? So what is cos y? Square root of 1 plus. Are you seeing that? Square root of 1 plus a squared x squared. So here it means we have a dx over square root of 1 plus a squared x squared, the value of cos y, isn't it?
Yes.
To be equals to d dy. Then you find that you integrate both sides. This a is a constant. If you factorize it out, you have that, isn't it? So if you integrate dy, you remain with y there,
Yes.
isn't it?
Yes.
But what is y? Y is sec inverse of
AX.
y is sec inverse of ax. So of course you can divide both sides of the equation by a. So what do you get? If you integrate dx over square root of 1 plus a squared x squared, then you are supposed to get 1 over a sec inverse of ax, of course, plus your c. Have you seen that? So integrating 1 over square root of 1 plus a squared x squared. That is what you are supposed to get. So can you now prove that? As an assignment, can you now prove that if you integrate, can you prove that if you integrate dx over square root of a squared x squared minus 1 is equals to 1 over a cos inverse of ax plus c. Can you now prove that? If you integrate dx over square root of a squared x squared minus 1, you're supposed to get 1 over a cos inverse of ax plus c. So, can you now list for me the standard integrals we've derived? I want to divide it into 2. When you put for me trigonometric, you give me the hyperbolic. So trigonometric we found, if you integrate dx over 1 plus a squared x squared, what do you get? You get 1 over a tan inverse of ax. Of course, plus c, isn't it? Plus c. Of course, plus c. So it means if you integrate dx, if the sign between them is negative, if it is 1 minus a squared x squared, then you are supposed to get 1 over a tan inverse of ax plus c. If the sign between is positive, it is tan inverse. If the sign between is negative, it is tan inverse. Have you seen that? Are we together? When you have 1 plus a squared x squared, tan inverse. Remember, you are putting 1 over a because in differentiation, you are multiplying by the derivative of the inner function. Are you seeing that? But in integration, you are dividing with the derivative of the inner. So you can see the inner function is x. The derivative here is 1 over a. You divide it by a. But for set, there was a which was in the numerator cancelled with the a which was in the denominator. Are you seeing that? Are we together? I have the next one. When you have integral of dx over square root of 1 minus a squared x squared, then you are supposed to get 1 over a sine inverse of ax plus c. Isn't it? Then it implies when the sign between them is now positive, then it goes to the same inverse. So it means when you have dx over square root of 1 plus a squared x squared, then you are supposed to get 1 over a sine inverse of ax plus c. Have you seen that? When the sign in between is negative, it is sine inverse. When the sign is positive, it is. These are standard integrals. Have you seen that?
Yes.
You need to master them. Next, when you have the integral of dx over x into square root of, remember when I have 1 plus tan squared y, I get x squared y. So plus tan squared y, I get x squared y, isn't it? So if you had your y was the tan inverse of ax, you bring here tan y is ax. So 1 plus, that is x squared. It was supposed to be tan. It was supposed to be tan minus. Good. So tan y is x squared minus. So if you have x into a squared x squared minus 1, then you are supposed to get tan inverse of ax plus c. You're supposed to get no tan inverse, you're supposed to get sec inverse of ax plus c. There's no 1 over a here, isn't it? When you have x into square root of a squared x squared minus 1, you're supposed to get sec inverse of. Are you together? Isn't it? You're supposed to get sec inverse of ax plus c. Because I see 1 plus times squared y is equal to sec squared y. But I'm looking for tan y, so it is sec squared y minus 1. Sec y, that is a squared x squared minus. That is what it is. So you move to the next one. If you have the integral of dx over x into square root of 1 minus a squared x squared, the opposite, isn't it? 1 minus a squared x squared, then you are looking for the sec inverse of ax plus. You are looking for the sec inverse of ax plus c. Then the last one, there are only 7 you will always encounter. Do you see that? The last one is the cos. Remember, for the cos inverse, it's just like saying but is having a negative, so you don't need that. Do you see that? But cos is very different. Cos means the sign in between inside the root there, isn't it? Because remember, when I add cos squared y minus sin squared y is equals to 1. So if I'm looking for sin squared y, it is that. So it is if you have square root of dx over square root. So if I look for sin, this goes there, come here. That is going to be square root of a squared x squared minus 1. Are you see? Is equals to cos inverse of ax plus c, 1 over a, isn't it? Are you see that?
Yes.
So if you have square root dx over square root of a squared x squared minus 1, you get 1 over a cos inverse of ax plus c. So those are standard. Those are standard. There are things you need to master. Okay?
Yes.
The things you need. Yes.
Under the paragraph,
Yes.
does it remain the same one with the last one?
This one.
The x roots x squared plus x squared minus 1. Then the other side.
This one is 1 minus. This one is a squared minus 1. Those are different. You see?
Yes.
Those are two different things. Yes. So you need to master all this. You see, I've mastered them because they are very simple. Simple things I don't have problem with, okay? You just master. So we are done with that. Let's go to the last thing. Partial fractions. Partial fractions. That one we've dealt with the inverse functions.